Someone asked, what is an MPI request? Well, you don't know, but actually, if we look at the header file, that's the header file there. That's the one that's included, the MPI.h header file. And if we look for request, oh, there we are. It is just an integer. So clearly, in this implementation of MPI, it numbers them internally. I don't know. So it's just an integer. There you go. But I mean, you shouldn't assume that, but that's interesting to know, just if you're interested. So if we look at here is the code for the message around a ring. So I will just check that it works. I'll use the C one for this. And this one uses the initialization. Actually, I'll do the simpler initialization where the pass on is where we initialize to the rank, because then we know that the answer should be size minus 1 over 2. So I'll recompile and let's run it on 4 tasks, and we get the answer 6, which is 3 times 4. 4 processes, 3 times 4 over 2. We run a different number of processes, we should get the right answer. Let's run on well, 10, say, and that's 10 times 9 over 2. So we're getting the right answer here. Okay, so that's good. The code seems to be working, and as distributed, the code just uses the first example of doing it. So we've just got a bunch of MPI variables here. The first thing we do is we have to compute who our neighbors are, and we call them left and rank, left and right. Left is rank minus 1, right is rank plus 1, but we have to close the loop. So if we're at the end, rank plus 1 equals size, right equals 0. If I'm at the start, then the left is size minus 1. So I need to do that to make sure that I form around in a ring. The next thing is, it's very, very important that, if I use this here, that you need 2 variables. Okay. We have the value we pass. So each iteration in the loop, we're sending a value to the right, and we're receiving a value from the left. Okay. Send to the right and receive from the left. What would be the problem if I just had a single variable here? I just called it passed on, for example. So if I did this, why would that be wrong? I have a single variable here, but actually you need 2 variables. You need one which you send and another one to receive. Why is that code incorrect? So, sorry, I was in the wrong window there. So exactly. Matthew said it would alter the variable being passed before send, and exactly what Dale has. Yes, so exactly. So you don't know when this send takes place. All you know is it's finished after the wait. Okay, you don't know when this takes place. It could happen straight away, but if it doesn't happen straight away, it might not happen till here. Then this receive will overwrite, and you could actually end up overwriting the data. The other thing I wanted to do was to show you that you could do. So let's go back. That should be add-on. Let's do it with the non-blocking receive. So let's do it this way. So we'll get I receive of the add-on. Okay, and now we have to put, instead of the status, we have a request here. We'll do an MPI I send of the pass on, and then we MPI wait. Okay, so now this is the other way around, not MPI S send. So this is the alternative one where we're saying I want to receive from the left, but that's the add-on, which I'm going to add on. Okay, I do the MPI S send of the pass on, and then I wait. Okay, so this is waiting for this receive to take place. And now I do the same code here, and let's see that. And we get the right answer. But what I can do now is do the wrong thing. For example, let's not wait. Okay, so let's do that and not wait. This has a problem now, which we're not waiting for this receive to have happened, and so we're possibly going to get funny answers. And not only do we get funny answers, but also Also, we get different answers each time we run. So this is the classic. This is the classic example of a runtime race condition where not only do you get the wrong answer because it's no longer 45, but we get different answers each time we run the program. I run it again, I get different answers. So we get the wrong. So that's actually that's only one processing to get it correct. But then it's still 40 hour processing 9. Yeah, that's just a. I think that's just a. Nobody got it right there. So it is completely random. And you'd also get the same thing if we just did, we just had one add-on variable. Let's put the weight back in, but so we just have this add-on here. Okay, we receive, we send, and then we just have the same variable. Okay. We'll see that we get again random values. Okay. If you anyway, that was just a display. So if you see that if you see that a classic, that is really the worst kind of bug, which, well, any bug gives you the wrong answer is bad, but this shows you that it depends on the runtime, and that is a classic symptom of having a problem with non-blocking communication. So non-blocking communication can be quite confusing because this I receive carries on potentially down to here. So you have to have two. So you have to wait to get the correct answer to make sure that it's completed, but you also have to have two variables. Otherwise, we are doing what we said we shouldn't do, is that we are touching that value, potentially altering it here. Well, we're accessing it, and we don't know when we do this send here if we're getting the old value or the new one. So I just thought it was useful to go through, and also it'd be nice to do the other example where you do a non-blocking send and a non-blocking receive, but that illustrated the concept. Are there any questions there? I thought it was useful just to spend 10 minutes going through that. So if I have no questions, I'll do the next lecture, then we'll have a break and I'll do the final lecture of the day. Let's just check I've got the right lecture up on. So what we're going to talk about now is something called Cartesian topologies. Now, actually, although we've only like a day and a half into the MPI course, you've done most of the core functionality. You've learned about how to run it, how to start up an MPI program, how to find out the fundamental things like rank and size. You've learned about send and receive. You've learned about collectives, and you've learned about non-blocking. And actually, for simple MPI programs, small MPI programs, by small I mean on small numbers of processes, that is often all that people need. However, the next two lectures talk about more general concepts in MPI. They talk about virtual topologies and derived data types, which are both extremely useful for writing real programs. I did debate at one point whether to carry on giving the virtual topologies talk, because years ago they weren't being used that much, although I think they're very elegant. But actually, in the most recent release of the textbook, which I mentioned, there's a nice chapter at the start where they go through the things that they got right in MPI, the things they think that distinguished it and made it better from previous message passing systems, the things which are core to its design and its success. And virtual topologies is one of the things which they noted there. And so I think it is still worth talking about. So we saw in that message around a ring example, that we had a communication structure in our program. Or we talked about it when we talked about the conceptual example of the traffic model. That basically here you imagined that your processes were arranged in a line, so that you had neighbors left and right. Now, by default, MPI COM world doesn't have any structure at all. I think it was just a bag of processes, a bag of, in that case, maybe 10 processes. However, when we write a real program in our mind, we think of those processes being arranged, in that case, in a line. But in more general, we might think of them being arranged in a 2D grid. And that's the example I'll use here. And it would be useful for MPI to provide you with some support over that, to allow you to tell MPI, look, my processes, you may think there's 16 processes, but they're actually arranged in a 4x4 grid. And that can then allow MPI to know more about your program and help you in writing a more elegant and hopefully more efficient program. So what virtual topologies do is they're a way of getting a process naming scheme which fits the communication pattern. So for example, if we think of our processes being arranged in a 2D grid, it's more convenient to think of the processes. So yes, it's an n-dimensional grid. Yep. So the question is, can the grid be 3D? The grid can be any number of dimensions. I just use 2D here because it's easiest to draw. But yes, in practice, you can do it for a 3D grid. And if you've got, for example, a 2D grid, it's much more convenient to talk about the process at position 3,2 than rank 17. It's useful to think of your processes having coordinates. So you have a naming scheme to fit the communications pattern. It simplifies the writing of code, and in principle, it allows MPI to optimize the communications, in principle. So how to use a virtual topology? What you do is you create creating a topology produces a new communicator. So what you do is you start off with, for example, MPI COM world, and you tell MPI, look, I want to create a new communicator which has the same number of processes in it, but I want them to be arranged in a grid, and that's called a Cartesian topology. And then once you've done that, it provides mapping functions where you can say who's up, down, forward, backward, left, right from me in the grid, and that allows you to think about the processes being where your ranks have grid positions rather than just this single integer which is your rank. You can say I'm the process at position 3,4. And so this is very convenient, and in practice, a large number of MPI programs do this. They do a regular domain decomposition. You think of a 2D, you think of your process as being a 2D grid. Now, MPI also supports unstructured topologies. They're called graph topologies. I don't cover them here, but if you're doing a problem where the communications pattern isn't structured, you say, well, I don't have a structured grid. My processes aren't in the 2D grid. They're in a much more general graph a relationship with each other. You can also specify that to MPI, but I'm not going to cover it here because it doesn't really fit into the flow of the lectures. But they're called graph topologies. What I'm talking about here are Cartesian topologies. So by example is a traffic model with multiple lanes. So previously we had the traffic model which only had one lane, and we thought about it being divided up into among p processes in a grid. But imagine we've got 4 lanes, okay? So we have 2 dimensions here. We have the lane dimension, which I'll think of as being the first dimension, I, and the cell dimension, which is now the second dimension, j. And so this is our traffic model. Again, so there are 2 distinct things here. First of all, we have multiple lanes, and so we'd probably want to distribute this first dimension across 4 processes. So we'd want to give each process a separate lane, but within that, if we have more than 4 processes, we want to distribute a single lane across processes. So we now have a grid of 4 by some number of processes to describe the assignment of the cells of this grid to the processes. If we're going to update this model, the other thing we also have to encode is the boundary conditions. If I'm this car here, who's my neighbor up the way? Well, it's this cell down here, because we have periodic boundary conditions. So if we update this grid, we know that these cars that move off to the right actually reappear on the left. And so it's not just enough to say I have a 4 by, let's say I have 32 processes. It's not just enough to say I have a 4 by 8 grid of processes. You're also interested in the boundaries, what happens at the edges. And the important point that this dimension here is periodic, it cycles back round, but this dimension isn't. if I say, so if I'm here and I say, who's my neighboring car that way, I get this guy here. But if I'm here and I say, who's my neighbor that way, there is no neighbor. Okay, this is a 4-lane road. I don't have a neighbor up that way. So I have periodic cyclic boundary conditions in that dimension and non-periodic, non-cyclic boundary conditions in that dimension. So the important point about these Cartesian communicators is not only do you encode the dimensions, how big your process grid is, and then it allows you to ask, who is my neighbor up, one down, one left, one right, but also you encode the boundary conditions as well. And MPI allows you to do them both. So if we think of in general here, we have a 3x4 distribution of processes. I would call this a 2D cylinder. I call it a cylinder because this dimension here is cyclic, so it wraps around on itself, but this dimension here is not cyclic, and so it doesn't wrap around on it. And this is a common problem. You might be simulating the fluid flow in a pipe here, where you have fixed boundary conditions at the edges of the pipe, but you imagine you have periodic boundary conditions along here, along the flow direction, to simulate an infinite length pipe. It's very, very common to have this mixture of periodic and non-periodic boundary conditions. So if I have 12 processes and I tell MPI they're arranged in a 3x4 grid, MPI then numbers them. So of course you always have your original rank, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But now you can think of the process having a grid position. And what MPI does is it does the obvious thing. It maps them in this way, that process 0 is in position 0, 0, process 1 is at position 0, 1. So this is natural to C programmers who are used to the second dimension moving fast. If you're a Fortran programmer, you would think it would be more natural for process 1 to be at position 1, 0. But MPI has to pick up. MPI uses the same convention in C and Fortran, and it uses the C convention. So if you're a Fortran programmer, you're going to have two things that confuse you here. One is the allocation, whether it's, you think of it as being row major or column major, is different from what you'd be used to. And secondly, the coordinates start at 0. Fortran programmers like to start at 1. But so those are slightly awkward for Fortran programmers, but there you go. So for example, rank 7 will be a position 1, 3. And this then allows me to ask, who are my neighbors? So if I'm rank 6, my neighbors in the first dimension are 10 and 2, and my neighbors in the second dimension are 5 and 7. Now, this isn't magic. You could do all this yourself. Yeah, you could convert this linear rank into a 2D grid by a bit of code and cope with the boundaries yourself. But the nice thing is MPI provides a standardized way of doing it. And that just allows you to write more elegant and more, hopefully more efficient, but definitely more legible code, a more readable code, because it makes more sense. Someone looking at the code, if they see you declaring a Cartesian communicator, will know immediately, oh, they're arranging their processes in a 2D grid. The second thing that MPI does is it assumes that if you're arranging your processes in a 2D grid, that you'll be communicating with the neighbors up, down, left, right, or in 3 dimensions in each of the axes. So that's what that's the assumption that that's what you're doing. So what we have is we want to tell MPI we've got 12 processes on a 3x4 grid. We also want to tell MPI that the first dimension here is non-periodic, but the second dimension here is periodic, it wraps around, and we can do all that. So the topology types are Cartesian topologies. Each process is connected to its neighbors in a virtual grid. Here I've used a 2D example. The boundaries can be cyclic or not. That's up to you, depending on your problem. You can actually allow MPI to reorder the ranks. So what MPI can in principle do is what we haven't talked about is when we run an MPI program, we just think of it as being a bunch of processes. But in reality, those processes will be mapped to physical nodes on a supercomputer. And the communications between, as we've discussed earlier, the communications between 2 processes on a node is much quicker than 2 processes on different nodes. And so you'd like processes that communicate a lot to be on the same node. Well, in MPI world, MPI has no information on how the communications happens. But once you've just defined a 2D topology, MPI thinks, oh, well, in this program, I can assume now that the communications is going to be nearest neighbor, and therefore I could renumber my processes so that so that the communications was more efficient. More communication will be on a node than off a node, for example. That's a logical renumbering. The processes don't move. What happens is you get a new rank in the new communicator. So if you allow MPI to reorder, it means that the rank in the new communicator is not the same as the rank in the old communicator. And that means something else you have to remember. Again, that's there in principle. In practice, I've never seen MPI do a particularly good job of this. But anyway, it's there. Graph topologies are general graphs, and they're not covered here, but you can look it up. The concepts are very similar. So first of all, to create a Cartesian virtual topology, it's called MPI cart create. So what I do is I call MPI cart create, which is to create a Cartesian topology. I give it an old communicator, which would normally be, say, MPI com world. I give it the number of dimensions, which previously was 2. I give an array of dimensions, which was 3 by 4. I give it an array of periodicities, which in that example is 0 or false and 1 or true for the first and the second dimension. I tell it if it's allowed to reorder. Reorder equals 1 or true says, yes, you have the freedom to give me so that rank in world, that my rank in the new communicator could be different from my rank in the old communicator, or false or 0 says no, if I'm rank 7 in com world, I have to be rank 7 in the new communicator. And you get back a new communicator, which is still a communicator, but MPI remembers it's a Cartesian communicator. So for the previous example, it would be MPI com world 2, 3, 4, 0, 1, reorder equals true or false, and you get back a new Cartesian communicator, which you could then, once you've got that, you can then you can ask within that Cartesian communicator, who are my neighbors up, down, left, and right. In Fortran, just the same, except the reorder is actually a lot. The periodic array and the reorder array are true logicals, whereas in C they're just ints. So that's the way it works. Does anyone have any questions about that? Just to, it's very important. If you allow MPI to reorder, you have to compute your new rank in the new communicator, and so you'll have multiplied entities. You'll have your rank in com world and your rank in the Cartesian communicator, which aren't necessarily the same. So I mean, it was quite easy to say that I've got 12 processes and I want them in a 4 by 3 grid. What happens if I've got 2,842 processes and I want them in a 3? So yes, the reordering is, so the question is, I hope I pronounced your name right, I don't know if it's Giove. Is the reordering completely automated? Yes. So MPI will have some algorithm to, so this is system specific. For this reordering to work, it has to know what the physical machine is. And so on the Cray, if this is implemented well, it will know that Archer 2 has 128 processes per node, and it will try and do a reordering to maximize for that. It's completely automated, yes. You don't know what the algorithm is, and different implementations will do different things, but the hope is that on your particular system, your MPI library knows about the physical characteristics of your machine, and then can do a good job. In practice, for regular domain decompositions, the sort of linear ordering typically works quite well. The first 128 ranks are on node 0, the next 128 on rank 1. That tends to work quite well. But I mean, you can play around with this. I haven't done it for a while because in the early on in MPI, it wasn't particularly well implemented. However, so I said it's fairly obvious to think that for 12 processes, a 3 grid might be good. But as I said, what about 2,842 processes in a 3D grid? Again, it's quite hard to work that out. So MPI, when you create the Cartesian topology, you have to say what the dimensions are. MPI gives you a helper function to give you a suggestion. You can specify what you want there, but most people would call MPI dims create. You give it the number of nodes, which is the number of processes. This is kind of an old terminology. You give it the number of dimensions, and it will give you back an array. So you do MPI dims create 12 into 2 dimensions, and it will give you back maybe 3 by 4 or 4 by 3. Of course, for these small numbers, that's fairly easy to do, but in a very, very large 3D, 4D program running on thousands of processes, it would be nice for MPI. It's just a helper function to give you a nice decomposition, and it'll try and give you something which is even. And so the thing which is the slight killer in this is you can see that we may have constraints. So, for example, in this example, I am constrained that I always want 4 processes in the first dimension, and I have freedom in the second dimension. So often you may have some constraints. So MPI DIMS creates a slightly unusual routine that the value of the dimensions has significance on entry. So that's a very good question. Matthew's asked, what if your number of processes doesn't fit neatly with the number of dimensions? I will come back to that. So if on entry the DIMS is 0, you're telling MPI it has complete freedom. So if DIMS is 0 before, you do MPI DIMS create, I've got 6 processes, I want them in a 2D grid, it will give you back maybe 3 by 2 or 2 by 3. Okay. If you do, I've got 7 processes, I want a 2D grid. There are only 2, because 7 is prime, 7, 1 and 1, 7 are the only valid ones, but it will give you that back. If you have a constraint, you say, I want a 3D grid, but the middle dimension has to be 3, just like in our traffic model, the first dimension had to be 4. I can do MPI DIMS create, I've got 6 processes, I want them in a 3D grid, and the middle dimension has to be 3, it might give you 2, 3, 1 or 1, 3, 2. However, of course, you can ask for erroneous things here. So without constraints, there is always a valid decomposition, because 1 by 1 by P is always a valid, and it's not a very interesting one, but 1 by 1 by 1 by P is always going to be a valid decomposition. But if you give a constraint, you can give an erroneous call. I said I've got 7 processes, I want them in a 3D grid, and I want the middle dimension to be 3, it will give you an erroneous call. So that's the important part about this call. A non-zero value in the DIMS sets the number of processes required in that direction. Make sure DIMS is set to 0 before the call. So MPI John Scott's asked, is there a structure which would allow you to handle, say, Hilbert curve? So you've got some space filling curve. So you'd have to use the most general one, which is the graph topology. So in a graph topology, you verbatim say the neighbors of process 6 are 7 and 5. So a graph topology is a more general, is the most general kind. So Matthew's asked, sorry, so first, John, did that answer your question? Yeah. So Matthew's, what does it do if there's an erroneous call? Well, I haven't talked about errors, but MPI, whenever it comes across an error, crashes and burns. So I don't really go into this in detail in this course, but when MPI encounters an error, it calls a default error handler routine. But when MPI encounters an error, it calls an error handling routine, and you can actually instantiate your own error handling routines. But by default, there's a default error handling routine, which is called MPI errors are fatal. So MPI crashes and burns whenever it hits. So any trivial error here, your MPI program will crash. Now that might seem a bit weird, but actually, if you've just said, I'm going to run for 20 hours on 1,000 processes of Archer 2, you actually want your program to crash rather than deadlock. So actually, although it's not very elegant, in practice, your program crashing, guaranteed to crash on error, is actually quite nice, because it tends to at least means you don't run for lots of time and waste. But yeah, whenever MPI encounters an erroneous call, it crashes. That's why C programmers often ignore the error code, or you really ought to check the error code of any MPI call. But by default, the MPI call never returns, because it discovers an error, sets an error code, but before it even returns to you, it crashes with this error are fatal. So there's no fault tolerance in MPI. Does that answer your question? It's actually the error handling in MPI is not as elegant as people might, but it's a pragmatic choice. If something's gone wrong, let's bail out and die so we don't, and we could even just try it here. I mean, if, for example, let's do the rotate thing. I'll do that at the end if I have time. So having created a Cartesian topology, you can then ask questions like, who are my neighbors, or mapping crosses grids to coordinate ranks. So for example, like an MPI cart rank says, what is the rank of the process at these coordinates? So you can say, you can give it a little array of coordinates, 0, 2, 3, 5, and MPI will give you back what the rank associated with those coordinates are. Same thing in Fortran. So you get back the rank associated with, and this of course has to be a Cartesian communicator. If you put MPI com world here, MPI would complain and say that doesn't make sense in MPI com world. The inverse is MPI cart coords, mapping ranks to process grid coordinates. So MPI cart coords says, given a rank, what are its coordinates? You have to supply a little array, and you get back the coordinates, which is nice. Same in Fortran. Yeah. This is the number of dimensions, and this is the coordinates. So, however, one of the slight weaknesses of topologies is, well, when MPI was first defined, although you could define a Cartesian topology, you couldn't say send a message up, send a message down. What you have to do is to work out who your neighbor is, up or down, or left or right. But when you did a send, you still did point-to-point communications to their rank. So what you end up doing a lot is, if I'm rank 6, I will call MPI cart rank. Sorry, I'll call MPI cart rank to work out my coordinates. I'll then add and subtract 1 to each of the coordinates in turn to find out who my neighbors are, and then I'll call MPI cart rank for those coordinates. Okay, so you'll convert from your rank from your rank to your coordinates. You'll do some arithmetic on the coordinates, and then you'll convert back from the coordinates to the rank, and then you can say, okay, the guy down the way is 10. I'll send to rank 10. That's slightly awkward. So MPI provides a nice routine called MPI cart shift, which says, who are my neighbors up and down in a particular direction? So you say, within this Cartesian communicator, who are my neighbors down to the left, down, and up? Okay, so this is rank. In the 1D case, this is rank -1 and rank +1. In direction is it the first dimension, the second dimension, the third dimension of the grid, and that starts counting from 0, which is a bit awkward. But if you want to specify the first dimension, you specify direction 0. Displacement is how far. Normally that would be 1. You're asking who your neighbors are, plus or minus 1. That's your nearest neighbors, but you could ask for who your next to nearest neighbors are, plus or minus 2. So this typically MPI cart shift is by far the most sensible routine. For each direction, it tells you who your neighbors are, down and up. And that's what you want to know. But you still use point-to-point send and receive to communicate with them. There are routines called neighborhood collectives, which I don't cover on this introductory course. But a neighborhood collective allows you to say, send a message to all my neighbors, where the neighbors is implicit from the Cartesian communicator. But the most common thing to do is to use the Cartesian topology as a way of calculating the ranks of your neighbors through this function, and then sending and receiving to them with point-to-point calls. The other question you might ask is, well, what if you ask for the rank of a non-existent grid? Well, look off the edge of a non-periodic grid. So in this example here, what happens if I say, who's my neighboring process there? Well, it's this process here. Who's my neighboring process up there? There isn't one. What does MPI do there? Well, it actually does, if you use this MPI cart shift, it does something quite elegant. It gives you the null processor. MPI returns a null processor. The rank is MPI proc null. That's nice because it means you don't have to write special code for the boundaries. So what you'd think is the processor which is near a boundary, you have to say, well, if I'm near a boundary, I don't send in that direction or I don't receive in that direction. Because you get this proc null back, you can send and receive to it. You don't have to write special, because if you send a message to proc null, it just disappears. If you receive from proc null, the receive returns immediately and nothing happens. So this allows you to write more elegant and general purpose code. So those are the two advantages of Cartesian communicators. They make the lookup tables easier to do, but they also implement this they respect the boundary conditions. Okay. So, so I saw Jovi said, would 2, 3, 2 work? I think the question was, I wanted 7 processes in a grid with the middle dimension 3, and 2, 3, 2 would be 12. So you're mandating that all the processes are assigned. So you're right. It doesn't consider a subset. Okay. Yeah. Or yeah. So having imagine that I've taken this domain and split it up into, I have a different communicator, sorry, I have a different process is assigned to each lane, okay? And the lane is split up. So imagine I had 8 processes here, 4 down the way and 4 across the way, sorry, 4 down the way and 2 across the way. So each process has 4 cells or 4 cells, okay? I run my code, and each process computes the number of cars that have moved. So each process has computed the number of cars that move locally. What collective call would I use to compute the total of cars that have moved? So I have MPI. I have each process has the number of each process knows, for example, a process contains these 4 cells here. It knows how many cars have moved in its portion of the grid. How do I compute the total number of cars that have moved in the whole simulation? I need to do a reduction operation, or reduce exactly. But what would the communicator be? That's absolutely right, go and reduce, but what communicator? I would use a communicator which contained all the processes. So that could be called world, or it could be the Cartesian communicator, okay? But that's fine. What would happen if I wanted to compute the number of cars that moved in each lane? Because there's a slow lane and a fast lane. How would I compute the total number of cars with a collective routine that have moved in that first lane? I can use MPI or reduce, but there is no MPI or reduce which says perform a reduction operation on all the processes in this lane. How can I customize MPI or reduce not to do a collective across all the processes, but only across the processes in, for example, a particular lane? And that's exactly. So Eric's got exactly. Could you split the Cartesian comm into slices? Absolutely. And so once you create a Cartesian communicator, it's often natural to say, I now want to split it into slices because I want to treat slices differently. You might have rows and columns of a matrix, for example, or here lanes means something. So I want to have a communicator which corresponds to a lane. And because I have created a Cartesian communicator, slicing it up makes logical sense. So MPI creates supplies routines called Cartesian partitioning. You can cut a grid up into slices, and new communicators produced for each slice. And then the important point, each slice can then perform its own collective communications. That's the most useful thing. MPI cart sub generates new communicators for the slices. So there's a slightly complicated way, use an array of 1s and 0s or trues and falses to specify which dimensions should be retained in the new communicator. If I have a 3D communicator, I could split it up into slices or into pencils. So, but there's a routine called MPI cart sub, which allows you to split a Cartesian communicator into arbitrary slices, and that can be quite a powerful technique. So MPI cart sub, you give it a Cartesian communicator, you say which dimension you want to remain. So in my example there, that would be 0, 1 or false true. You want the second dimension to remain. I want to split across the first one, and you get back a new communicator where each process ends up in a communicator for its own lane. So you could call this com road, and this could be com lane, where that's a communicator with everyone in the same lane is in the same communicator. It's quite nice. So the exercise on the sheet, it's slightly contrived because in the message around a ring example, it's really not hard to compute your neighbors as rank +1 and rank -1 and cope with the boundaries by yourself. But I would like you to rewrite that to use a one-dimensional ring topology. It at least gets you familiar with the syntax, even if the code, it actually might be more complicated to write the code and do it by hand. Of course, you don't need to worry about doing the, if I'm rank size -1, my neighbor is 0, because that will be done for you automatically by the cart shift on the Cartesian topology with periodic boundary conditions. So are there any questions on that? If not, I'll do a quick example of something I'll show you that I should never do, which is live coding, where I haven't tried it before, but let's try this. We'll share the... So what I'm going to do is show you what MPI does with errors. So let's look at the rotate.c. Okay, let's just say, let's get rid of this check here. Yeah. So now we'll have an invalid rank. Yeah. So right will be invalid. Right will be, for one of the processes, right will be invalid. So let's see what happens there. Oh, horrible. Yeah, well, you get fatal error, invalid rank. And you see that this error causes all processes to terminate, even though, so this is, you know, this is, although it's a local error becomes a global error, if you see what I mean. Yeah. And you might think, I really ought to do, so that's clearly an error from MPI send. Yeah. Yeah. I could do error equals MPI send if, and I haven't talked about this, but it should be error is not equal to MPI okay. That, so I need to do an, I'll need to have an int error up here. That is what you really ought to do. Error equals MPI send. If error is not equal to success, print send error and then do something. But what actually happens is MPI send detects the error, calls the default error handler, which causes everyone to crash and burn. So you will never get to this line. So MPI programmers tend to be rather lazy and don't check error codes. You really should check the error codes, but people tend not to. So let's compile that just to show. And if I run it, I'll do it on fewer processes. Let's do 4. We never got that error. Yeah. If you see here, that print never occurred because it was killed before we got that invalid rank value 4. Well, so we get a quite a nice error message here, rank 3 in com 0. So we do get quite a lot of information here, but fatal error in PMPI send, and yeah, errors are by default fatal in MPI, and that's probably what you want. I don't want this code to deadlock. I'd rather it just crashed horribly. So I thought I'd mention that there. Hope that was useful. So what we're going to talk about here is derived data types, and this again is a very important part of MPI. You know, in real codes, although they use things like reals and integers and double precisions and such like, often have more complicated structures in them, like SC structures, for example. So what we're going to cover here is how to send and receive data in MPI, which doesn't immediately conform to the default, which is a block of 10 integers, for example. So MPI has two classes of types as the basic types that we've already talked about, and those are basically, they're different in C and Fortran, they just map onto the native language types. So, you know, you have MPI int or MPI integer, MPI double precision. But the derived types which MPI provides, and the ones I'll cover here, are vectors and structures. So you can define your own derived types, which are made up from the basic types. So a basic type is used in this way. If I have an array of 10 integers, integer x10 in C or Fortran, I could send all 10 values by doing this. MPI send x 10 integers or send x 10 MPI integer. Right? Exactly. That's fine. Okay, no problem at all. We did discuss this a bit before. How would I send the first 4 values? We actually had this conversation and during the first, someone asked a nice question, but just briefly, how would I send the first 4 values? Yeah, x4, absolutely. And I've actually been slightly pedantic here. I've said address of x04 or in Fortran x14, but it's the same thing. Okay. What about the 5th, 6th, 7th, and 8th values? Counting 1, 2, 3, 4, 5. Or how would I do that? So not that block, but this block here. Yes, in Fortran x54, so I want to start at x1, 2, 3, 4, 5, or in C, the address of x of 4. So that's all fine. So we have some flexibility there. But what about this? What happens if we want to send the 1st, 2nd, 6th, and 7th elements? How could we do that? And it will turn out that's the thing we often want to do in MPI, I mean, in scientific and technical programming. Anyone think, well, we can do that. We know enough to do it, but you can't do it immediately. What could be the approaches for sending that data? There's a couple of solutions. So John Scott says something like, yeah, unfortunately, the you can't specify that. So John's right, you want to send x2, x3, x6, and x7, but all you're allowed to pass to MPI is a pointer. So MPI expects contiguous data. So Alex says send twice, yes. So you could do 2 sends here. What's the disadvantage of 2 sends? You're absolutely right. You could do send x1 in C, x2 in Fortran, and each for the count of 2, twice the overheads, okay? And sends are slow, exactly. So that will take. I could also pointer arrays. Well, don't quite know what you mean there. There's a more simple way of doing it. We could do it with 1 send. I need a bit of extra coding, but I can do something else. Yeah. So the answer. So you can do copy in, copy out. So the 2 obvious solutions to this are either do 2 sends, which as people have pointed out is slow, or do copy in, copy out. Copy in, copy out is inelegant. Okay. So MPI actually supports ways of natively sending this data with a single send, but they're called vectors. Also, what happens if it wasn't an array of integers? It was an array of structure mystruct x10, or in Fortran type mytype x10. Okay, they're not integers. They're things called that's going to be a real problem. Yeah, because of course MPI as a library has no idea what mystruct is. So, but MPI does allow you to do that. It allows you to create structures which correspond to language constructs like derived types in Fortran or structures in C. So the motivation is the send and receive calls need a data type argument. We have predefined values for the predefined language types. But what about types defined by a program, structures in C or user-defined types in Fortran? And the other thing is that the send receive calls take a count parameter. What about data that isn't contiguous in memory? Now you might say, why would anyone ever want to send this data here? Well, it turns out that that corresponds exactly into subsections of 2D arrays, or in general, n-dimensional subsections of n-dimensional arrays. But for illustration here, I'm going to do 2D arrays because they're simpler to draw. So what you do is you define a new type in MPI. You can define new types in MPI. The user calls various setup routines to describe the new data type. Why do we have to do that? Because MPI is a library, not a compiler. If MPI were a compiler, it could look at your code and say, oh, okay, David has defined a structure. I can send that because I know what it looks like. MPI is a library, not a compiler. And what you do is you get a new data type handle. The predefined ones are MPI double, MPI integer, and all those things. So it's never, I could have my MPI my new type, and that's really nice. So, example, in the traffic model, in a real traffic model, your car would probably be a structure of type car or vehicle. Let's call it vehicle, and it would have lots of parameters. You know, its occupancy, its maximum speed, its braking. It would be nice to do MPI send 5 MPI vehicle. And you can do that, and it makes the code much more legible. All you have to do is tell MPI what a vehicle looks like. So the derived types have the same status as the predefined. You can use them in any message call. You have to be careful for reduction operations, though. If you define an MPI vehicle and pass it to MPI or reduce, MPI is going to say, "I've never heard of an MPI vehicle. I don't know how I add them together." But you could define your own reduction operation. And I didn't go into that in detail, but you can register your own reduction operations, and this is when you might want to use them. So it turns out that all derived types in MPI are fundamentally stored a list of basic types and displacements in bytes. So that's at the very lowest level how MPI defines them. And for a structure, the types may be different, because a structure is almost by definition a collection of different types of object. For an array subsection, the types will be the same, but the displacements will be weird. And you can define new derived types in terms of both basic types and other derived types. So you can layer them up. So I could define a vector which of vehicles, for example. So what do you mean by extend? So Alejandro, MPI defined types could be Fortran extended types only known at runtime. What kind do you mean? Do you mean like an MPI? I mean, yes, a derived. Do you mean like a derived type, which is the equivalent of a C structure? Abstract Fortran types. So yes, they can be. I'm not very good with very modern Fortran and things like abstract types. Oh, this is all probably yes, probably. In principle, yes. In practice, there may be. So because what you do is you define what the derived type, you define what the type looks like to MPI at runtime. So if the type is only defined at runtime, then you should be able to do it. But there are a lot of subtleties with Fortran types, which I'll maybe mention briefly. But I don't see any reason why you shouldn't use on abstract types, because the MPI routines are called at runtime. So this is how MPI defines it. The very lowest level, a derived type, when it's flattened out, is the basic types 0 to n-1 and their displacements in bytes. But that's a kind of a low level. It's a useful concept to be aware of. So the simplest derived type is just a number of contiguous items from the same data type. It's called MPI type contiguous. So I specify the count. This could be my standard example is 4. I could do. My program might send around blocks of 4 integers a lot of the time. It could mean something. It might be nice to have something called a block 4, which was 4 integers. So I do MPI type contiguous 4 MPI integer and store that value in a type of called in a variable called MPI, called block 4, for example. So I can define a single type which is 4 integers. And so when I want to send 4 integers, I can do MPI send 4 integer or MPI send 1 block 4. So I could use MPI send with MPI integer and count equals 4, or I could define a new contiguous type of 4 integers called block 4 and use MPI send with type equals block 4 and count equals 1. And this explains a question that someone had from the previous lectures, where surely they said send count and send count and receive count should be the same when you do a scatter. Well, not necessarily, because I could do an MPI scatter with send type of 1 block 4 and receive type of 4 integer, and that's completely legitimate because they match. Okay, a block 4 contains 4 integers. So MPI doesn't do MPI when MPI does type matching. It only looks at the actual contents of the message. So I can send 1 MPI block 4 and receive it as 4 integers, and that's perfectly allowable. So when I start playing around with derived types, you can see you could do a gather and a scatter where the send type and the send count and the receive count were different, but it still worked because the send count was 1 block 4 and the receive count was 4 integers. So it's slightly technical, but that can be useful. Again, these could be useful intermediate stage in building more complicated types. So it's not particularly interesting, but it's the basic one. However, vectors are the most useful ones in terms of this. So a vector data type in MPI is defined as this. We have a repeating pattern of a block and a gap, a block and a gap, which repeats many times. Now, we can define that in many ways, but MPI defines it as a triplet. A count, because there's two blocks. A stride it's not the gap. The stride is the distance between each successive block. So the gap and the block length is the length of each block. So count equals 2, stride equals 5, block length equals 3 defines this pattern where we have two blocks, each of length 3, separated by a sort of 5. Or you could say the gap is the stride minus the block length, but MPI is defined. So hopefully it's clear that this triplet of numbers 2, 5, 3 defines that data type. Element, 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 gap, gap, element, element, element. Now, you might think, why is that useful? Well, the important point is that corresponds to a 2D subsection of a 2D array. That is a vector, a repeating pattern of block, gap corresponds to subsections of 2D arrays. And we often want to send and receive boundary data. So we want to take subsections of 2D arrays in codes. So what is a vector type? Why is a pattern with blocks and gaps useful? Well, a vector type corresponds to a subsection of a 2D array. So we're going to have to think about arrays are stored in memory. This gets all horrible because C and Fortran use different conventions. I'm going to use statically allocated arrays in C here. If you dynamically allocate your arrays using malloc, then I'll cover this in the final day, but I'm going to assume that you've done something very simple here, because once you start dynamically allocating arrays with malloc, things get much more complicated. For Fortran, it's fine. For Fortran, you can use static or allocatable arrays because allocate is part of the Fortran language. Unfortunately, malloc is just some random runtime standard library routine in C. We can come back to that later. But so people are going to complain. This is how I'm going to draw my arrays. I'm going to draw my arrays such when I draw them such that I goes along and J goes up. I know most people like to draw them as matrices where I goes down and J goes along, but I have a slightly philosophical objection to that, because a 2D array is not a matrix. A matrix is it. So I mean, and most of my 2D arrays aren't matrices. When I have a 2D array, it's mostly an area of land in a weather forecasting code. The natural mechanism is XY. In most codes, 2D arrays are XY arrays representing a physical decomposition, and people draw X go along and Y goes up. So I think I should go along and J should go. If you like drawing them the other way, you'll just have to transpose it in your head. It's not a big deal. But I'm going to draw the arrays so that I goes along and J goes up, because I'm thinking of a coordinate system. So for a C array, I would draw it like this: X3, 3 there, X2, 3 there, X1, 3 there. A Fortran array, it's just shifted by 1. So that's how I'm going to draw them. This is going to affect what we call along and down. And actually, you can choose to draw arrays however you like. It doesn't change reality. You can draw them as first index right, second index up. That's coordinates, X, Y. First index down and second index right is a matrix. But if you're a graphics program, you would do first index right and second index down, because that's graphic scan lines. So, but regardless of how you draw them in memory, the layout of how you draw them, the layout in memory is in C, Xij is followed by Xij plus 1. And in Fortran, Xi plus 1, Xij is followed by Xi plus 1j. Now you can call that row major or column major if you like, depending on how you, but this is the true statement. And it's unfortunate that C and Fortran have different conventions, but they do. It's history, I guess. Depending on how you draw them, this can appear row major or column major. So what happens when you actually declare an array? If I declare an array in C of x44 or Fortran x44, what the compiler actually does is it gives me 16 elements, and it has a mapping of the indices ij into these 16 elements. And the way I've drawn it in C, the mapping is vertical. It goes x00, x01, x02, x03, x10, x11. And in Fortran, it's the other way around. x11, x21, x31, x41. So it's just, C and Fortran have this difference in opinion between which way. But the important point is, if you declare a 2D array in this simple way, int x44, the data is contiguous in memory, And there's a different convention for the mapping of the 2D space to the 1D space in C at Fortran. If we now start drawing some pictures, you'll see that if I have a C array 5, 4, the 3 by 2 interior subsection, the way I've drawn it here, is a gap of 6 integers to it's a 3 by 2 subsection of a 5 by 4 array is 3 blocks of 2 elements separated by gaps of 2, which is a vector as I draw it at the start, which is nice. And in Fortran, it's just the same, but a 3 by 2 subsection of a 5 by 4 array is 2 blocks of 3 elements separated by gaps of 2. And it turns out we often want to do things like this because often in an MPI program, we'll have done a domain decomposition like we did in the traffic model. But in the 2D domain decomposition, the halo data isn't a single element; it's a whole line of pixels or data. So we'll need to send and receive entire lines or columns or rows of data. So these are the equivalent vector types. Okay, in C, that 3 by 2 subsection of a 5 by 4 array is block length 2, count 3, and stride 4. In Fortran, it's block length 3, count 2, and stride 5. There's just a twiddling around of the elements. So I can create it. So to construct a vector type, it's MPI type vector. You give it these triplets, count, block length, stride. You give it the old type, which here might be MPI integer, but could be something more, could be anything. And then you get back a new data type. MPI type vector, count, block length, stride, old type, new type, IR. You get back a new type. And so the only thing you might, so is that clear? We're going to define a new type which corresponds to this pattern, this repeating pattern of block, gap, block, gap. And that will be useful for directly sending 2D subsections of 2D arrays without multiple sends and without having to do copy in, copy out. Okay, so, but actually, we've lost some information because these subsections had a leading gap here. Yeah, we've lost that information. So actually, this vector data type specifies a 3 by 2 subsection of a 5 by 4 array, but not which one it is. But when we do a send or receive, the data that is sent depends on what buffer you pass to the send routine. Just like if we want to pass elements, the 5th, 6th, and 7th elements of an array, we pass the starting address of the address of x4 or x5 in Fortran. Where this, I think of these vectors as templates, and where they're placed, that you just pass the address of the first element that should be sent. So for example, okay, if I define this vector 3 by 2, if I want to send this subsection here, I started at x11 in C or x22 in Fortran, which is that guy there. Or if I want to send this, I can use the same vector, it's the same pattern to send this subarray here. I just start at a different position. So that's, you know, those are useful. So that would allow you to send this data in a single send. Okay, and MPI will do all the packaging up and for you. So it's more elegant than copy in, copy out. It's more elegant than, and it's more efficient than doing multiple sends. So there are various data type inquiry routines. You may be used to find out how big a derived type is, the extent and distance from first to last. I mean, there are various inquiry routines, but they could be useful. So that's vectors. So does anyone have any questions about the vectors? And there is an exercise on the sheet which is to do with vectors as well. So I can send and receive. The important point is when I do a send of a vector, I can do MPI send one MPI vector, and that could contain a huge amount of data. It could be megabytes long, but I'm only sending one of them. Okay. Okay. The second data type you encounter in real, which you need to do in real programs, are structures. So, do you still specify the vector size? I don't understand what you mean by the vector size. Maybe I didn't explain it quite. Could you just elaborate? No, because, okay, if I define a vector, imagine I use this definition. Let's take the C. I define a vector with block length equals 2, count equals 3, and stride equals 4. That corresponds to this data. It corresponds to 6 elements. if I send one of these, I send those 6 elements. Is that clear? So I would send one vector and it would send all these 6 elements because the vector contains all these multiple elements. Is that, maybe that's not your question though. So yeah, you can send multiple vectors, but annoyingly, if you send 2 vectors, there's no trailing gap here. So defining a vector with count equals 3, block length equals 2, stride equals 4, and sending 2 of them is not the same thing as defining a vector of count equals 6, block length equals 2, and stride equals 4, and sending 1 of them. Because in the first case, you lose the gap. It abuts them right up to each other. So actually, sending multiple vectors, you can. It's well defined what it does, but it's rarely useful. It doesn't do what you think it would do because of the unfortunate way they've been defined in MPI. It's always a bit of a headache. It's annoying. Does that answer your question? So in practice, you normally send 1 vector because you define it to be the right size. So you can send multiple vectors, but it rarely does what you want because it doesn't maintain the gap. The second vector will do elements 0, 1, 4, 5, 8, 9, and then it would do element 10, 11. It would I counted that right. 0, 1, 4, 5, 8, 9. Yeah, anyway, it would butt it up without a gap. So you can send multiple vectors, but it doesn't do what you think it would do. Yeah, it makes sense. It's annoying. It has a whole bunch, it's a whole world of pain. So the other thing you might do is the structure. So C and Fortran have almost equivalent syntax for defining compound objects. C calls them structures. Fortran calls them derived types. I have an int value multiplied for 3 double precisions. This could be a particle. This would be an identifier. Is it an oxygen molecule or a hydrogen molecule? And this might be its position in space, X, Y, Z. The difficulty is the exact storage format of this object is not defined by the language. Different compilers do different things. And a compiler is allowed to insert arbitrary padding between successive elements. So what most C compilers will do is it will insert 4 bytes of padding here so that this double precision value sits on a nice 8-byte boundary. So the size of this structure will be 32 bytes, not 28 bytes, although it only contains an integer. So this is a problem, because how can MPI know what your compiler has done when it's a pre-compiled library? Unfortunately, what you have to do is you have to tell MPI, you have to describe this structure in gory detail to MPI. You need to tell MPI the byte displacements of every element. It's nasty, but you only have to do it once. It's a setup phase. So you have to do things twice. You have to define this structure in your code, and you have to also explain what it looks like to MPI. The nice thing, though, is although different compilers do different things, it's guaranteed it will always do the same thing. So if I declare 2 of these, they will look the same. So it's not allowed to say, Mondays and Fridays, I'll put some padding, and Tuesdays and Wednesdays, I won't. Basically, it's a static decision. So if we want to define this structure to MPI, we have to tell it the count. I'll come back to what that is. The array of block lengths, the array of displacements, the array of types, and we get back a new type. And it's the same in Fortran. Now, actually, remember what this is. It's an integer followed by 3 doubles. The first 3 arguments are fairly obvious. Count is 2, meaning we have some integers, then some doubles. The array of block lengths is 1, 3, saying that we have 1, then 3, and the types are integers and doubles. So this defines the structure logically. It says we've got 1 integer followed by 3 doubles. But unfortunately, we need to tell MPI more than that. We need to tell them where these things start in memory. This is nasty and hacky, but you have to do it because, again, MPI is not a compiler. How do we compute the displacements? We need to create a compound variable in our program, explicitly compute memory addresses of every member, and subtract the addresses to get the displacements. C does guarantee that there's no padding here, so the address of the variable is the same as the address of the first element. Fortran probably doesn't actually. But you have to do a bit of setup, and it's a bit awkward, but once you've done it, you can then send and receive 3 MPI compounds. The other reason why you do it this way is, again, in principle, MPI supports different compilers in the same program. So the sender might have defined the structure differently from the receiver. Now, we never do that nowadays because we use the same compiler, the same hardware everywhere. But the sender and the receiver might have had different definitions of the structure. This allows you to pass a structure portably between different compilers, because the sender, they both define what it looks like and it packed and unpacked correctly. Bit of a technical point, but if you're a Fortran programmer, you'll say, I can't do this because I'm not allowed to ask about memory locations in Fortran. Well, they give you a routine MPI get address, which gives you back the address. And now we get into nasty things that once you start taking addresses, these things may not fit into 32-bit integers. They won't. So we have to have a special type in C MPI aint, which will be a long, I don't know what it is, but some variable big enough to store an integer, an address. In Fortran, we have a new kind equals MPI address kind. So it's all rather nasty and hacky, but there is no way around it because MPI is a library, unfortunately. But having done this setup, we could do MPI compound. I could do send and receive 5 MPI compounds. I could create a vector of compounds. Okay, so all that works nicely. One technicality: once you've created a data type, if you're going to use it in message passing calls, you have to commit it. You have to stamp it. So Eric's saying, if you're using C++, could you use a serialization library and just send the serial object? Yes, I guess you could. I'm sure that's what things like Boost and that do. Yes, you could. You could just send. Does it just become a bunch of bytes? Is that how? I'm not a C++ programmer. I presume a serialized object is just a bunch of bytes. Yes. I think it would be more elegant to do this way, but yes, you could do that. It's up to you. You could do that. So if you have dynamically allocated arrays, it's even more complicated. But in Fortran, there are no issues. It doesn't matter in Fortran if you allocate array, because allocatable in Fortran, because arrays are part of the language, it doesn't matter if you create them dynamically or statically. They're just arrays, and it all works fine. There are subtleties with Fortran arrays I'll cover on the last day, but in terms, there are no subtleties with this part of it. Fortran arrays are just Fortran arrays. They're very nice. The problem is with C arrays, people dynamically allocate them with pointers to pointers, and you get weirdness going on, which I'll cover. But Fortran's all fine. Fortran's much easier for arrays. Does that answer your question? Yeah. So if you're going to use an MPI data type in a send or receive, you have to commit it, which kind of stamps it. But there you go. So the exercise is actually to modify the message parser ring exercise, calculate 2 separate sums, a rank and a floating point sum, but use a struct data type. So I want you to create an integer followed by double precision number as a structure and send or receive that as a single object. So you'll need to define, what do you want to call it, MPI my struct. If you're more interested in the multidimensional array stuff, then 8.2 covers type vector. So if you're a Fortran programmer, I'm sure you're more modern programmers, but I tend not to use Fortran derived types much. But again, both exercises are relevant, but I would think it's worth looking at the vector as well, because that illustrates how to do sends and receives of array subsections where you've defined them with vectors. If you want to do, Eric, someone was asking about. John was asking whether you can send multiple vectors. If I told you to do a 3-dimensional subsection or a 3-dimensional array, you would probably say, I'll do vectors of vectors. But unfortunately, that doesn't work very well. It's all a bit. So I don't mention it here. Maybe I should. But if you want to do a general, so for 2D, it's nice. A 2D subsection with 2D arrays, just this nice vector block gap pattern, and we use MPI type vector. However, it became clear earlier on that people wanted to do more complicated things like that. Vectors weren't quite fit for purpose for higher dimensions. So there's a routine called MPI type create subarray, which is a general, very simple to use routine, which creates an n-dimensional subsection of an n-dimensional array. So if you want to do, if your arrays are 3D or more, I would recommend using MPI type create subarray. I'll just so I'll show you one of our PhD students actually created this website called Rookie HPC, which has very nice stuff on it. I'll stop this and share his. So just to give you the, might be useful to know. So this is his entry on this website, MPI create subarray. It's very, very simple. You pass it the number of dimensions, the array, how big the big array is, how big the subsection is, and where it starts. They're the obvious things to do. So you would say, I've got a 10 by 7 by 8 array. I want a 4 by 2 by 3 subsection, which starts at position 2, 3, 1. And it just gives you a data type which corresponds to that. You have to tell it if you're calling from C or Fortran, because of course what it looks like depends. So order is MPI order C or order Fortran. But it is actually a very simple routine. And unlike vector, it also includes the trailing gap. So it actually knows where it starts. It includes, it does everything for you. So that's an alternative, and you that's an alternative routine which you would need to use for 3 or 4 dimensional arrays, just because the vectors aren't really fit for purpose for that. Okay, so those are all the lectures. The bit I'm going to and we're going to have a break now, and then the exercise practical session from 1600. If we look at the timetable, I'll maybe just show you what we're going to do. For the final set on Wednesday, I'll start off with a little quiz, which is quite fun, hopefully. Interactive quiz, anonymous quiz, where we can explore some of the issues we've talked about. Then I introduce something called the case study, which is an image processing example, which is the nearest I could find to something which was computationally intensive, relatively representative of real programs, but was understandable in a short time. And I'll introduce that. You can have a look at it. I'll give out solutions. Then I'll give a tricks and tips lecture from 11:30 to 12:30, where I will basically give a bunch of things I've talked about. How do you cope with malloc arrays in C? There's a whole bunch of different bits and pieces in there. It's things which I've noticed people get wrong over the time. So that's just a general tricks and tips lecture. Then we'll go back to the case study, and in the afternoon we'll be around just to answer individual questions. You can carry on doing the practicals if you want, but we'll be around, a couple of us will be around at least to take questions if you have any more general questions. And if you have specific questions about your own codes, we can do breakout sessions and look at that. We're happy to do a breakout session there. There will be a reservation for that day, so you'll be able to develop and run codes. But I'll speak to you again at 9:30 on Wednesday, when we'll kick off with the MPI quiz. But for now, that's the end of the lectures, and the practical session, which starts at 4 p.m., will be staffed by William. I think William's around.